Good morning to you all, and you're welcome to yet another interesting time with us. It promised to be an interesting technical session today. Uh, my name is Enoch Ochai. I'm a guidance, navigation, and localization engineer with Omefi Technology, a subsidiary of Unicorn Group of Company. So today's technical session, we'll be looking at how does a robot know where it is. And in today's technical session, in the next 30 to 40 minutes, we'll be done. And after a technical session, there'll be rooms for question. So I crave your indulgence to please listen attentively. So our topic today is, how does a robot know where it is? We'll be hearing about robots. As we all know, we have different kinds of robots. We have the wheel robot, we have the humanoid robot, several kinds of robots. So there's a question before us this morning. How does a robot know where it is? And helping us to answer this question, we'll be looking at a probabilistic approach using Gaussian distribution, sampling, and Monte Carlo localization. So I just want you to give me attentive ears as we look at this topic together this morning. How does a robot know where it is? Now, when we talk of robot localization, knowing where a robot is, let's actually look at this. Looking at this image here is just giving us a complete idea of what happens when a robot moves around. First of all, the robot has to know where it is. That is where the problem of localization comes into play. The robot knowing where it is, the problem of localization coming into play. Also, the robot has to know its environment. That's to say, mapping, taking cognizance of what is available in the environment, things that are placed in the environment. So the robot has a map of its environment, where each and every object is located, where each and every object is placed. That's actually a problem of mapping. It gives rise to the robot having to plan its paths, because for a robot to actually know where it is and also having the map of the environment, for the robot to actually move to a particular destination from its starting point or from its location, it has to definitely plan its path. So the localization problem, the mapping problem, the path planning problem, also the robot has to give commands to its wheels, to its motors, to actually move them to its desired location. Seeing all these things together, it actually gives us an idea of how a robot moves or how a robot operates in our environment. First of all, we're having the problem of localization, where the robot is. Secondly, we have having the problem of robot understanding its environment. That's the problem of mapping. Thirdly, we have the issue of the robot having to move from its from its set location or its starting point to a desired location, a problem of path planning, and also giving commands to its motors. That's motion control. But today, our major goal is, from the topic, our major goal is, how does a robot know where it is? So today, majorly we'll be looking at the problem of localization, getting to know where the robot is. So looking at this video in our next slide, we'll be seeing different robots, the mobile robots, the drone, and the humanoid robot, getting to localize itself properly to perform tasks. Because I wanted to understand that for a robot that is not properly localized, for a robot that doesn't know where it is, and mistakes are inevitable. The robots running into faults is inevitable. So localization is a problem that has to be solved, and that has to be settled first. Robots knowing where it is. So let's look at the video of robots that has proper knowledge of its location and how they are able to move around in the environment. This is actually a SWAT robot. Having proper localization, having to know each and every place an obstacle is positioned, having to know, get an understanding of the map of the environment, and it's actually able to properly localize itself and make this navigation effectively. As you can see, we have different view of the robots. And for localization to be proper, for localization to be possible, definitely the robot must actually get to know its map. All right, let's look at. All right, thank you. Let's look at the drone. Just like I told you initially, robot localization is very important, and it's something that we can't just neglect. The robot getting to know where it helps the robot to move around in its environment properly. So let's look at this drone and how localization is important for a robot to actually move around in its surrounding, irrespective of obstacles, irrespective of so many things that are in the surrounding. The robot is able to know where it is, know where the obstacles are, and is able to navigate its way. Let's look at this drone.
Or is this more excitingly demonstrated than in the thrilling sport of drone racing? It takes years of dedicated practice to reach a professional level, as pilots must rely solely on visual information to navigate. These pilots showcase incredible skill and reflexes, maneuvering their drones with remarkable precision and agility. Recent research has shown that reinforcement learning policies can outperform drone racing world champions using the same hardware. However, unlike human pilots, these policies continuously estimate an explicit state from known gate positions, the camera feed, and inertial measurements. In this work, we tackle the challenge of learning vision-based drone racing using an end-to-end reinforcement learning approach that eliminates the need for IMU data or explicit state estimation. Our method focuses on developing a purely vision-based control system, demanding high simulation rendering efficiency and effective transferability to the real world by utilizing inner gate edges as visual cues for navigation. To achieve seamless transfer from simulation to the real racing environment, we use a gate detector that identifies and outputs gate edges for the drone's navigation. This visual input serves as...
Okay. First of all, we looked at that of a mobile robot. Now we looked at the drone. Lastly, we're looking at that of a humanoid robot. These are different set of robots. And it's just like answering the question of how does the robot understand its location. But before we answer that question, let's look at how a robot are able to properly understand its location and perform tasks in the environment. So we've looked at a mobile robot, we've looked at a drone, and now let's look at the humanoid robot, how the concept of localization helps the robot to properly position itself in the environment and perform tasks. So let's look at the humanoid robot. Okay, that's actually a humanoid robot. That's actually an Atlas from Boston Dynamics performing operation in the environment. And I want you to understand that those operations can never be possible without the robot knowing where it is. So this leads to our next question. How does a robot estimate its location in an environment filled with uncertainty? I want you to know that for the robot to autonomously move around, the robot to make actions to perform tasks around, it has to be able to localize itself properly in the environment. So this question now is trying to tell us, how does a robot estimate its location in an environment filled with uncertainty? So it's giving rise to why localization matters. Why localization? On top of localization, just like I've said earlier, is robots knowing where it is. Localization is the robots knowing where it is. Just like we humans, when we're in a particular location, we are aware of the location we are due to the fact that we have a map of the environment, we know our surrounding, and we are aware of everything that's happening. So we as humans, the problem of localization is not a problem to us. So now answering this question for the robot, how does the robot estimate its location in an environment filled with uncertainty, which gives rise to the question why localization matters. I want you to understand that localization is crucial for autonomous decision making. As we all know, we have different types of controls for the robot. We have a control where we do that remotely. A remote control where we have to manually like give inputs and give commands to the control from a sensor, or we send command to the robot and we control it remotely. And also the robot has to having to move autonomously, making decisions. So localization is crucial for autonomous decision making. A robot having to move autonomously on its own just by sending commands to it. Robot not knowing where it is actually dangerous, because errors in localization leads to a navigation failure. For a robot to move around the environment, do things, just take for instance, you have a manipulator that you want it to pick, a manipulator or a human robot that you want it to move a distance to perform some certain tasks, or a mobile robot that you want it to move around to perform some certain tasks. Robot not knowing where it is, that's localization. Having a localization issue leads to error in location, which leads to navigation failure. Just like I told you initially, first of all, a localization is paramount for the robots. Next, mapping. That's to say, the robot has to be aware of its map, knowing each and every location in the map or the world where it is located. And also path planning. You can't actually plan an effective path if the robot doesn't know each and every location of the object in the world, and also the location of where it is in the world. So localization is of paramount importance for autonomous decision making. So next we'll be looking at call concept in probabilistic localization. Call concept in probabilistic localization. And when we talk about call concept and probabilistic localization, we're looking at three stuff here. We're looking at one, understanding uncertainty in robotics. Two, we're looking at Gaussian distribution and sampling. Then thirdly, we're looking at Monte Carlo localization. First, we're looking at understanding uncertainty in robotics. Secondly, we're looking at Gaussian distribution and sampling. Then lastly, we're looking at Monte Carlo localization. So these are core concepts we're looking at in probabilistic robotics. First of all, let's look at understanding uncertainty in robotics. When we talk of uncertainty in robotics, I want you to understand that you can't take this out in robotic system. Uncertainty will always be there in any robotic system. You can't, as in, have an ideal robotic system where you have perfect sensors giving you perfect readings, where you have like, okay, you set a robot to perform an action, the robot does that effectively. Uncertainty definitely are there in robotic system. So it gives rise to the next question: what are the sources of uncertainty? What are the sources of uncertainty? I want you to understand that we have, just like I told you initially, we have different types of robots: the wheel robot, the human robots, the manipulators, and the rest. So on top of sources of uncertainty in robotics, one, we get this uncertainty from wheel slippage. Take for instance, we set a robot to move a motion, and the robot is set to move. You can't tell what might happen in the next motion. There might be oil spillage on the floor, and this might lead to wheel slippage. And this wheel slippage is actually an uncertainty that has been introduced into the robotics, the whole system. So first of all, before understanding where the robot is and how to localize the robot in the environment, first we have to understand where this uncertainty is coming from. And just like we've just seen here, first we have uncertainty from wheel slippage. That's to say, the wheel not having a perfect rotation due to it being slipping. So that's to say, in robotics we call it the odometry reading is not actually perfect. So secondly, we have uncertainty from sensor noise. Uncertainty from sensor noise. A sensor is designed to actually give a reading, and you see it misbehaving, giving erratic readings and the rest. So this uncertainty are bound to happen. So just take for instance, you set a sensor, an ultrasonic sensor that is supposed to measure distance. And this time the ultrasonic sensor is given to you is the noise from the sensor reading is very high. Just like, for instance, you set the robot to perform a task. When it sees an obstacle that is 30 kilometers, the robot is supposed to stop. But the ultrasonic sensor reading, the noise from the ultrasonic sensor reading is so high that it exceeds 30 kilometers before it exceeds 30 kilometers before the robot is able to like sense and stop the robot. So sensor noise is actually an uncertainty in robotics, and it has to be looked at. And lastly, we look at uncertainty from unknown environment dynamics. Anything can happen. Just like we have different types of sensor, we have the LiDAR, we have the camera, and these different types of sensor, they work based on they work effectively based on different environment. You see most of the times a camera not being able to work effectively when it is raining. So we have unknown environment dynamics. So these are sources of uncertainty in robotics, and they have to be looked at. So next, we'll be looking at the question, how do humans make sense of uncertainty? How do humans make sense of this uncertainty? When we have wheel slippage, when we have noises from sensors, how do humans make sense of this uncertainty? Just take, for instance, a sensor reading that is supposed to say, the reading from the sensor is supposed to give you, okay, let's say a temperature reading from a temperature sensor is supposed to give you 35 degrees Celsius. But you get to understand that it's not actually giving you 35 degrees Celsius. It's giving you around 32, 37, 34, 33, 36. So these are actually uncertainty, sensor noise. So now those erratic readings you get from the sensor reading. How do humans make sense of those sensor noise or those uncertainty? I want you to understand that probability is how humans make sense of uncertainty. Probability is how humans make sense of uncertainty. So those erratic reading, those noise we get, those wheel slippage, all those uncertainty that are being introduced into the system, probability is how we humans make sense of those uncertainty. And we've seen that Bayes have helped us to formalize how we make sense of uncertainty given data. And this data can take any distribution. I just want you to understand that this noise you get from sensors, there are uncertainties, and Bayes as a scientist has helped us to like formalize this make sense of this uncertainty given data. And this data, just like I told you initially of a sensor reading for the temperature sensor, the sensor noise being gotten from the temperature sensor, the 35, the sensor noise, just for instance, the true value, the sense, the temperature sensor is supposed to give is 35 degrees Celsius. And you see it's giving erratic reading of 36, 37, 34, 33, and the rest. So with the help of probability, we have been able to make sense of this uncertainty. We have been able to know if the sensor reading is supposed to be 35, or it's supposed to be 36, or it's supposed to be 37. With the help of Bayes help us now to formalize how we can make sense of all the given data. And I want you to understand that noise, 35, 34, 33, 37, and the rest, it can take any distribution. As we go further, you understand properly what I'm trying to talk. It's taking any distribution. It can take any distribution, but we've seen it it has been proven that a perfect distribution has been set for it to take. We've seen different types of distribution the sensor noise can take. It can take a Poisson distribution. It can take a beta distribution. It can take a Gaussian distribution. It can take a gamma distribution. But over time, it has seen that, okay, this erratic and sensor noise that has been given, that is being given from the sensor reading, 80 to 90% of this data by Gaussian distribution represent its in nature. That's why next we'll look at the next slide. We'll be looking at a type of distribution that represents this sensor noise, which Bayes has helped us to formalize, to make sense of our given data. We'll see that Gaussian distribution is perfect for it, because 80 to 90% of the sensor, the data being gotten from the sensor reading is actually true in nature. So we're looking at Gaussian distribution in robotics. What is Gaussian distribution in robotics? Just like I told you initially, the 34, the 35, the 36, the 37, but the true value for that temperature reading is 35, 37 degrees Celsius. But you see it having erratic reading. noise from the sensor giving different reading, but the true value is 35. So what is this Gaussian distribution in robotics, which we've chosen to actually represent this noise from this temperature sensor we've gotten? So Gaussian distribution models data where most values are close to the average, which is the mean, and fewer values appear as you move away from the mean, forming a bell shape. You get from the ultrasonic, from the temperature sensor, definitely there's a reading, there's an expected reading you want to get, which is the 37 degrees Celsius. But you see it's having different. When you model this noise, you have a distribution based on this formula. When you model the noise based on the formula, there's a mean, which is the center of the data, where the peak of the curve occurs, and also the standard deviation, which measures the spread of how wide or narrow the curve is. You see, most data, okay, let's say for you to say the sensor reading is actually accurate. Okay, let's say for you to say that the temperature sensor is actually accurate, you see that it's actually giving close readings to its true value. If the true value that is supposed to measure at that particular, if the temperature is supposed to be 37 degrees, you see it giving 36.5, 37.5, 33.5, sorry, 36.5, 37.8, 39, 36.5, and the rest. So you see the value actually close to the true value. And one of the value actually close to the true value like that, you see that the distribution now, the values gotten from the sensor are actually very close to the mean, which is the true value. Why the standard deviation just tells us how far apart the values are from the mean. So with the help of the Gaussian distribution in robotics, we're able to like have a look at or a representation of this our noise. It has been formularized here, the f of s with this formula here. We are able to get like a distribution, which is this. So once the values are close to the mean, the expected values are close to the mean, you have a very steep curve. But once they are very far from the mean, you have a curve that tends to be very flat. That's to say your sensor reading is very noisy. But if you have a curve that tends to be steep, that is trying to tell you that, okay, most of my values that I'm getting from my sensor are very close to the true value. So next we'll be looking at sampling and representing belief. Sampling, which is representing belief. Okay, now, Gauss actually helped us to mathematically represent this sensor reading. But I want you to understand that there's also a which is also using particles. So with sampling, we represent this belief with particles, which exact computation is feasible in a real-world environment, and sampling approximates the probability distribution. And we have different types of sampling. We have the random sampling, we have the importance sampling, and we have the resampling. So next, we'll be looking at this video. This leads us actually to the state-of-the-art localization. Just like I told you, we have different forms of localization, and we have the belief from what I've told you initially can be represented by scientists. Erratic readings, so this is our noise from the sensor, and we actually do that by Gauss and distribution. So point in time where particle was actually used to represent and where particle was actually used to localize an object, and it was done perfectly in the year 1998. This was actually a research done by, and it was led by Sebastian Thrun, one of the great minds of robotics, and he also led the Google self-driving car. Looking at this robot, we'll go back in time and understand localization and where it's coming from.
Smithsonian project, the goal for Minerva is to move around of the exhibits to the visitors while avoiding the people around her in the exhibit cases. Here, we see a depiction of Minerva's collision avoidance software attempting to find a route through the people surrounding her, shown as green dots.
So if
For
as you can see
navigation,
there,
Minerva
particles
uses a
are
map.
actually used to represent the
Unlike many
sensors we need.
robots in the past, she was driven around the empty museum, and using the measurements from her laser sensors, was able to construct a map of the museum. We can see an over Minerva uses the map to determine where she is by comparing points in the laser data to points in the map. She determines her most likely position and orientation by finding the most probable corresponding.
All right. This leads to a Monte Carlo foundation. I want you to understand that when it comes to localization and understanding where a robot is, trying to get an actual position for a robot, we have different foundations to it. And based on background knowledge and based on what has been built over time, we have the Bayes filter and the Kalman filter. These are foundational knowledge. For the Bayes filter, this Bayes filter helps us to update the system state based on new evidence, and it uses Bayes theorem to combine the prior knowledge and observation. And this helps us track changing states over time with uncertainty. So on top of the Kalman filter, which was actually based on the Bayes filter, it helps us to minimize error between two Gaussian, that's the prediction model and the measurement model, using analytical formula. I want you to understand something important. What it does, how it does its localization, and how it estimates position for robot is based on analytical formula. So for the Monte Carlo for the Monte Carlo localization, we actually move further from using analytic formula. Here we actually simulate the system, we simulate the robot, we simulate it, and we actually use particles. That was why we're talking about sampling initially. We actually use particles here. So instead of representing this uncertainty or this uncertainty or the models in our system with analytical formula, because when you say okay, a robot is supposed to move, first of all, you move the robot based on a model. You predict the robot. Okay, the robot is supposed to move. There's a distribution is supposed it takes. You analytically represent that to the Gaussian distribution. And also you measure to confirm as the robot actually moves to that particular location. So there's also a measurement model to confirm what you actually predict. You are predicting from the odometry you get from the wheels, or the motion model you get from the robot in general. So for instance, if it's a human robot, there's a motion model you get from the human robot, a mathematical motion mathematical model for the robot to move. So you predict the model, so you predict the robot motion, and also you confirm from the measurement model. So what the Kalman filter is trying to do is it's trying to use mathematics, analytical formula. Okay, there's a prediction model, it's having a Gaussian distribution. There's a measurement model, it's having a Gaussian distribution. What it does is it minimizes the error between these two models to have another Gaussian distribution that gives us the true value. But for the Monte Carlo now, it's actually a foundation based on Bayes and Kalman, which actually updating our belief. So next we'll be looking at we're looking at a Monte Carlo localization where a robot is simulated, and we see that the robot belief is represented using particles. And each particle represents the robot possible pose and weights. On top of the robot possible pose, we're talking of posing here, we're talking of the robot location, that's the S and Y coordinates, and we're talking of the robot orientation, where it is facing per time. So each particle that is being simulated here for the robot represents each possible pose plus weight. Weight trying to tell us, okay, is this particular particle close to what it's supposed to be? If it is not close to what it's supposed to be, there's a weight that's been attached to it, a number that's been attached to it to actually increase it based on, okay, we are certain that it is close to our true value, we increase the weight. It's not certain to our true value, we reduce the weight. So each particle, we have a possible robot pose and a weight for it. So on top of the process of this Monte Carlo localization this basically with simulating the robot, having particles, having different forms of the robot in the environment, so that we have like a possible pose for this different object, and also we have a weight to assign, a number to assign to the robot to actually increase, okay, the belief if it's actually true to what the robot is supposed to do. So for the process, for the Monte Carlo localization, we have first to predict the motion model. We have the sensor model to update. First of all, the motion model predicts. We have the sensor model update. Also, we have to resample. Resampling in the sense that, okay, when we have these particles being simulated, okay, definitely there are some particles that are of lower weights. We have to discard them. Why particles that are of higher weights that have importance to us? That's where important sampling comes in. Sorry, that's where the important sampling, pick all those particles that are of importance to us, that have higher weights, they are close to the robot true location. We pick them and we resample them. So next, we'll be looking at Monte Carlo localization in robots, and we'll be looking at this key step. First of all, we'll be looking at initialization, we'll be looking at prediction, we'll be looking at correction, and we'll be looking at resampling. First of all, when we talk of initialization, particles are spread uniformly across the map due to the robot's unknown initial position. If the initial pose is known, particles are concentrated locally. That's to tell you that, okay, for you, if you actually know the initial pose for that particular robot, the particles you simulate in the environment, okay, you simulate 1,000 of them to actually, okay, check for the robot position. What this particular initialization is trying to tell you that if the initial pose is known, you see that particles are concentrated locally around the robot, because those other particles you've simulated, truly they will come to confirm the robot location, that this is the robot, where the robot location is where it is truly and where it is located. So you see, most of those particles that are simulated around are truly concentrated around the robot. Next, there's a motion object, which actually gives rise to prediction. The robot moves forward, the robot moves, and each particle is updated based on the motion. Model plus noise, simulation in real world, movement and uncertainty. Next, we look at correction, which is the sensor update. First one, predicts, we correct, sensor measurement are compared against the predicted measurement from each particles. And particles whose precision match the actual measurement receive higher weights. Just like I've told you, for a particular robot, we have the robot pose and the weight. Particles whose precision match the actual measurement receive higher weights and are allowed to stay. And also, prediction also takes place again. They move. When they move, particles with lower weights are discarded. Particles with higher weights are allowed to stay till most of the particles are accumulated around where the true location of the robot is supposed to be. Then lastly, we're looking at resampling, which is an important sampling. Particles with higher weights are more likely to be selected. Low weight particles are replaced by duplicates or better ones, refining the belief. So next, we're looking at a system where we'll be looking at the simulation of Monte Carlo. We're looking at the simulation of Monte Carlo and how it is used for robot localization. As you can see, as the robot moves there, it's like simulating the robot. Plenty of the robot is being simulated. And once these particles are around in the world, you tend to like, okay, predict the robot motion. When the robot motion is predicted, you measure from the sensor. When you measure from the sensor, we tend to do resampling. Particles that you see that, okay, truly they are off from what the sensor is actually giving are discarded, while particles are truly, that are truly close to the sensor reading are actually left. And also prediction also takes place again. Resampling also takes place. Then you update with the sensor reading. So next, let's look at why Monte Carlo for robots. Why Monte Carlo for robots? Now I want you to understand that Monte Carlo is flexible, is simple, and is accurate. It works with any model, even if it is non-linear or complex, or use complex probability distribution. No need for simplification. And also, we see that it's easy to implement. Just sample random values and compute results. Just like for the Kalman filter uses the analytical method, whereby you have to like, okay, get the Gaussian distribution of the prediction model, we get the Gaussian distribution of the measurement model, which we get from the sensor, and we tend to minimize the error. So for the Monte Carlo, we don't actually have to go to the analytical formulas which are actually complex when it comes to like computationally intensive. So for the Monte Carlo, it's simple. We just have to simulate our system, easy to implement, just random particles, random sample, random values, and compute results. No need for solving equations analytically. and also it is accurate. Estimate get closer to the true value as more samples are used. I want you to understand that we get a perfect localization for the Monte Carlo when you use when you use numerous samples. Just as we understand from the law of large numbers. When we use numerous samples, that's when it gets like a perfect localization for the Monte Carlo. Now, just a classical example of what this large number is when it comes to Monte Carlo localization. Just take, for instance, we're supposed to like guess the height of okay, let's say you are supposed to get the average height of everybody in Nigeria. If you're supposed to get the average height of everybody in Nigeria, if I decide to like, okay, first of all, if I decide to like, oh, I want to get the average height by measuring the height of each and everybody in Nigeria, I know it will actually give me a good answer, but it won't actually it will be efficient because I have to waste time getting to check each and everybody, then compute the average together. But the best way to do it is, first of all, I have to pick a sample. So that's what this Monte Carlo localization is trying to tell us. We take a sample of the population. Now, taking the sample of the population, we have to be critical when taking the sample of the population. I want to take the sample of the population. I can't just go to a particular location and just like pick, okay, in this location, I'll just go and pick these persons and start measuring their height, then use it as a generalization to the fact that that's the average height for the whole population. No. First of all, I have to do that picking randomly. Because if I just do it, what if I go to a particular location and most of them there are just short persons? I won't actually get through the true average height of the persons that are in Nigeria. So another idea when it comes to this is random sampling. Random sampling, in the sense that I have to pick randomly. I have to go to different locations and pick randomly, getting different random samples. So when I pick these different random samples, the next thing I have to put into consideration is me taking much of the sample. That's where the law of large number comes into play. That's where the law of large number comes into play. Me taking different samples. So the more samples I take, the better for me to estimate the true height of the different persons in Nigeria. So Monte Carlo Monte Carlo localization does this with sampling and estimating the robot's position. So next, we'll be looking at the state-of-the-art localization. Particle filter is a cutting-edge probabilistic localization technique for mobile robots. It estimates a true robot's position. And if you see this image here, this is actually a research that was carried out recently. It was a research carried out last year by a university, and I want to understand that Monte Carlo localization is actually a state-of-the-art localization, and it's currently used in research to find positions and estimate the true locations for robots. I want to understand that particle filter is actually the state-of-the-art method for robot localization. We've seen different ways of localizing robots. We've seen the Bayes rule. We've seen the Kalman filter, which uses the analytical method. But this particle filter, it gives more accurate results, even in complex environments. And with integrity monitoring, it helps to make the robot navigation safer and more reliable. So in conclusion, we've looked at uncertainty in robotics, and we know that uncertainty is inevitable in robotics. And secondly, we looked at the Gaussian distribution model, which models uncertainty mathematically. We've chosen the Gaussian distribution model because this Gaussian distribution, the uncertainty and the noise we get from our sensor or from our environment, the Gaussian distribution represents 80 to 90% of truly what we have in nature. And also we looked at sampling, which is applied to Monte Carlo localization. We've seen that this sampling helps us to approximate complex beliefs. Where we actually, okay, we pick from the population, we pick through values that are close to the expected, we pick values that samples that are close to the expected value, then we discard the other ones by assigning weights, higher weights to the ones that are close to the value, and lower weights to the other ones that are not close to the true value, and discarding them. And lastly, we've seen that Monte Carlo offers an effective real-time solution to robot localization. Thank you for listening.